I'm now going to calculate the Lorentz transformations, which tell you how the coordinates in different inertial frames are related to each other. The coordinates are the spatial Cartesian coordinates plus time, and an event is something that happens, something that has particular values of the Cartesian coordinates and the time. We're going to stick to standard configuration, which has the two coordinate systems oriented in the same way, coincident at time 0, so that the origins are on top of each other, and with the frame S' moving in the positive x direction with velocity v. This is just a simplification that helps us do the calculations. We're going to assume that the relationship between the coordinates in the two systems is linear. That is to say that the S' coordinates are linear functions of the S coordinates, including time. Now we know that the origin of the S' coordinate system is at position x equals vt in the S coordinate frame because it's been moving with velocity v for time t in that frame. Consequently, the x' coordinate, which must be 0, that's the only possible linear relationship between x and t and x' that has x' equal to 0 when x equals vt. Gamma is some unknown, which we are going to calculate. Now, of course, we've already seen gamma, and it'll turn out to be the same one, but at this point, we're in the business of deducing the value for gamma. And we can make the same argument for the origin of the S system in terms of the x' coordinates. The origin of the S system has x coordinate equal to 0, x' coordinate equal to minus vt, because from the point of view of the S' system, the S coordinate origin has been moving with velocity minus v along the x' direction for time t'. So the only way x can be equal to 0 when x' is equal to minus v t' is if there's this linear relationship. We can argue that the two gammas should be the same gamma should occur both ways round because of the symmetry of the situation. It should make no difference whether you're traveling to the left or to the right. Now let's consider a flash of light that occurs when the coordinate origins of the S and S' systems are on top of each other at t equals t' equal to 0. So instantaneous flash at that point. There's then a shell of light that propagates outwards in 3 dimensions. The x' coordinate of that flash of light is ct', because at time t' it's been traveling with the velocity of light c. And similarly in the S coordinate system, its coordinate is ct. Now what is odd here is that the shell of light has the coordinate origin of each coordinate system at its center. And that's because the speed of light c is the same in both coordinate systems. It's a very odd thing, but it's a consequence of the second postulate. The center of the spherical shell in the S coordinate system is the origin of the S coordinate system, and the center of the spherical shell in the S' coordinate system is the S' origin. We now substitute these equations into the x and x' coordinate transformations that we just derived. We now multiply those two expressions together. Multiply the left-hand sides and the right-hand sides. And cancelling the t' times t from both sides, where it's obvious that the positive sign is the correct one from the expressions we previously derived. So what we've got now is an expression for the unknown gamma that occurred in the linear relationship between the coordinates. So these are our final transformations, including the explicit expressions for gamma. The next step is to derive coordinate transformations for the time. We now use the transformations for x and x' to obtain those for time. And substituting the expression for x' into the equation for x, we now have an equation that we can solve for t'. Now we have to use results that is a bit long-winded to work out, so I'll just tell you what it is. You can check it for yourself, but the thing in brackets there. So if we substitute that in, so now we have an expression for the time t dash in the s dash system of some event that in the s system has time coordinate t and position coordinate x. Finally then, writing out the Lorentz transformations that we have derived, where the latter two follow because lengths perpendicular to the motion don't change, therefore coordinates don't change. And where we found that gamma, now we could have made a different argument in order to obtain the s coordinates in terms of the s dash coordinates. All we would have found is that the coordinates swapped around and the sign of the velocity changed, because in the s dash system, s is moving with velocity minus v. These are called the inverse Lorentz transformations, and the sign of the velocity changes. They're called the Lorentz transformations because they were actually derived by a number of people, but particularly by Hendrik Lorentz, many years before Einstein derived them. They were derived on the basis of trying to understand how electromagnetism would work in different frames, the very thing that Einstein talked about in the introduction to his first relativity paper. The thing that was new for Einstein is that he understood what they meant. For Lorentz and others, these x's and x dashes were just mathematical abstractions. What Einstein realized is that they apply to actual space and time as measured by rulers and clocks. This was his fundamental insight. The value of the Lorentz transformations is that we can apply them without thinking in detail. If we use the physics that they contain, length contraction, time dilation, and the relativity of simultaneity, we have to be very careful about how we apply each of those pieces of physics to a given situation. We can reduce that situation to the behavior of events whose coordinates we know, and then the transformation of those coordinates between inertial frames. We really don't have to worry about the details of the physics because it's all contained in the Lorentz transformations. This means that it reduces the kinematics of relativity to an algorithmic process, which is very good if you want to avoid confusion.